Okay, so I think in the lecture you guys started the electrochemistry. So this experiment objective is to measure the potential of the voltaic cells. So shown below in this diagram here is the constructed voltaic cell in our lab. So you will see a real picture after this one. So here I show a voltaic cell constructed by zinc and copper. So the chemical reaction is zinc as a solid react with copper solution. So you can see the blue color here, and they'll become zinc 2+ in aqueous solution, which is a transparent no color solution, and the copper solid. And by convention, the cell voltage is always positive. Redox pair here is the zinc solid get oxidized to become zinc 2+. That's the oxidation process that occurs on the anode. And the reduction occurs at the cathode. So it will be copper 2+ get reduced to copper element. And the shorthand notation for this one is zinc 0. That means element zinc, and there is a phase divide. So two different phase. This is a solid, this is the liquid, and this is the concentration. And this double line means a salt bridge. Okay, so this is the copper solution, and then element copper. In this lab, it's pretty straightforward. We'll use a LabQuest unit to measure the cell potential. It's very similar as measuring a battery voltage by a digital multimeter. Remember, the definition of the cell potential is the cathode half cell potential minus the anode potential. However, there's a little difference here. In our case, our concentrations are not always 1 molar. Thus, we are measuring the E cell potential, not the potential at the normal conditions. Normal condition means 1 atmosphere pressure, 298 degree Kelvin, and the 1 molar concentrations. We're measuring at the 1 atmosphere pressure and at the room temperature, but we are not measuring at the 1 molar concentration. So in order to calculate the E0, E0, that's at the normal condition, we can measure the E value and using the Nernst equation. Since we know out, you'll find the concentration ratio from the lab report template. Then by this equation, we measure E, and we know the Q value. We can calculate the Q value through the concentration. We know how many electrons transferred. Then we can calculate the E0, which is the standard cell potential. Okay, and we are assuming a temperature of 298 Kelvin for all the measurement. So this is the first cell we use to do the measurement. In the template that you'll see, we use 6 different cells. And I want to point it out that for cell 4 and 6, electromaterial is carbon. Okay, so carbon is an inert electromaterial, and in 4 and 6, the carbon does not participate in the redox reaction. The redox pair for cell 4 will be I- and I2 element. And then for cell 6 will be IN2+ and IN3+ at 0.1 molar concentration. So how do we measure the cell potential? It's quite straightforward. So just as the digital multimeter, we plug in the probes. So you can see the probe at one side that can be plugged into the LabQuest, and the other side will be 2 alligator clips, and turn it on and clip the alligator clips onto the electrode. Then we can take the digital measurement. But sometimes you can get a negative measurement. So for example, if we are using the copper-silver pair to do the measurement, so for the zinc-copper pair, we can get the positive measurement. For the silver and the copper pair, we'll get a negative potential because in this case, the copper is no longer the anode, the copper become cathode. So in this case, we'll just simply switch the polarity of the alligator clip, then we can get the positive measure. We measure the potentials for all 6 cells, and their values are listed in table 1. So that's the table 1 in the lab report template. All the cell potential are measured here. So in table 1, you are going to calculate the standard cell potential. And remember, by convention, the cell potential is always positive. So the copper electrode is not always the cathode. When we have the cell potential and the concentration are all also given to you guys. So they are, except the zinc copper pair is 1 molar. Other concentrations are 0.1 molar. So you have the concentration and you can calculate the Q value. And then by writing out the redox equation, you can figure out how many electrons are transferred. So you can figure out the N value here. And then you have the experiment E value, and you will be able to calculate the standard VE for the cell. The first one is for the zinc copper electrode. The value is already calculated for you guys. Once again, remember, in order for the potential to be positive, the copper will not always be the cathode. And in table 2 here, we assign the copper half cell potential to be exactly 0.00, and we'll calculate the other half cell potential. So here in the table 2, you need to list the cell description and list the anode reaction and the cathode reaction. Make the assumption that the copper cell is at 0.00, and then based on the cell potential, you can calculate the other half cell potential. So for the zinc copper case, the standard cell potential, we calculated to be 0.900. And since we assign copper to be 0, then we can calculate the zinc half cell will be negative 0.9. So that's table 2. And for table 3, we make a different assignment for the half cell potential. So now in tables 3, we don't want to say copper is still 0. We want to use the standard hydrogen electrode as our reference. So the standard hydrogen electrode will be 0 in this case. And when we use that as a reference, the copper electrode becomes 0.337. We still apply to the same equation at this one as we use in table 2, but the copper here is no longer 0. It becomes positive 0.337. Okay, so positive 0.337, and the electrode is still 0.9. And then we can calculate the new anode potential. So in this case, the anode potential is negative 0.663. The first one is down. You'll calculate through reaction 2 to 6. Data table 4 will use the data we calculated from table 3. So we identify the half reactions and list the reaction in order from strongest to weakest oxidizing agent. You will be provided with literature values, and you will make a comparison and find out the percentage error. So the literature values for the reactions are listed here. So for example, in the copper case, the literature value is 0.337. You're given for the copper is 0.337, then the percentage error here is 0%. Table 4, you'll do a data comparison between the literature value and your experimental values. Table 5, in this case, you have the experiment E-value, and you're going to calculate the delta G through this equation, where you know the number of electrons, and the F is a constant. The values are given here. So you measure the E naught, and you can calculate the Gibbs free energy. Okay. There are a couple ways in terms of calculating Gibbs free energy. One, you can base on the battery potential we measured from the experiment. The other, we can calculate the delta G through the definition, delta H minus T delta S. And the delta H and the delta S are provided here. Remember, this is for 25 degrees C. In the equation here, the T is in the unit of a Kelvin. So you need to convert this 25 degrees C to Kelvin, and then plug in the calculation. You can find out the delta G. And once you have the delta G calculated, compare that with the delta G you got from potential measurement, and then calculate the percentage error. On Canvas, the experiment procedure is provided, and this PowerPoint slides are provided. And there is also a report template with all the data in table 1. So you have the data in table 1, you'll calculate and fill out the table 2 through 5, and make sure all the values are typed, and the calculations can be done handwritten.